Hello, everybody. I hope you're doing well. So this is the video lesson for section 6.3, which is on conservative vector fields. And this very exciting sounding theorem that is named the fundamental theorem of line integrals. All right, so let's get started on conservative vector fields. All right, section 6.3. The title of this section is conservative vector fields, but this section is pretty much more about the fundamental theorem of line integrals. All right, so I will of course tell you what this means, but as always, whenever I talk about or when I start a new section or a lesson on calculus 3, you notice that I start with something related to that new topic in calculus 1. All right, so I have 2 points I would like to review. And one is, well, the fundamental theorem. We already have one, right? And it's called the fundamental theorem of what? Of calculus. All right, and it actually has 2 parts, and they both tell you that the integration and the differentiation are the opposite procedures. That really is the essence of the fundamental theorem of calculus. Sometimes I abbreviate this as FTC. The one that I will be presenting today, sometimes I abbreviate as FTLI. Of course, they are both fundamental theorems. The fundamental theorem of calculus, the first part says the derivative of the integral is basically the function itself, right? But the second point is what I'd like to emphasize, and that is, and if you have used this hundreds of times already, if you have a function, integrable function f, the integral from a to b of fx dx is equal to, the way you calculate this, and by the way, this is not the definition. The definition is that this is the limit of the Riemann sum, as we talked about last time. But in order to determine the value of this, or in order to evaluate this, what we often do is to calculate this by finding a function whose derivative is this lowercase f. Now, we call this capital F, and we say capital F is an antiderivative. Okay, and in fact, you can use any antiderivative. Usually the antiderivatives are, with plus c, and of course, the plus c will disappear when you do the subtraction. So you pick any antiderivative, capital F, of the derivative of the function lowercase f, and then we calculate the definite integral this way. So this is not, this is not hard, or at least you have used this many times, and this is nothing new to you, right? Let me again tell you what this is. dx of f is equal to the lowercase f. That is the understanding when I write this. Okay, so the point that I'd like to make here is this: the integral, this integral, the integral of lowercase f from a to b depends not on the values of any other points between a and b, but depends only on fa and fb. These are capital letters, capital letter f. Okay, so it only depends on the values of the antiderivative at the 2 endpoints. Okay, and this is important because the same kind of idea happens with the fundamental theorem of line integrals. Okay, now number 2. Last time we saw this, but if you have, let's see, you have 2 different paths from point A to point B. Let's say this is a curve called C1, and this curve is called C2. Okay, and so you have 2 curves, C1 and C2, both going from A to B. What we mentioned last time is that the, let me go ahead and write this in the first notation, the first way we denoted this. This is the line integral. What do we call this? This is called the work integral of f with respect to or along the curve C. Sometimes it's called the flow integral. Sometimes it's called the circulation integral if C happens to be a loop. Okay, but this is what we typically write as FDR. Remember that? And so it sounds presidential, FDR. It's basically the same thing. But this value actually depends on the path. Okay, and in other words, what I'm saying is that the value of FDR, the work integral on C1, is generally different from the FDR of C2. Okay, so it does depend on the path, even though both paths start at A and end in B. And this is true. It's not equal to each other in general. Okay, but I hinted at this last time that for some vector fields, the value of this line integral, or maybe I should just go ahead and write this as FDR. All right, so what I'm going to say is that normally this work integral is path independent. The integral of FDR is path independent, path dependent. So if you take different paths, C1 and C2, the values are usually different in general. But for some family or some particular a subset of vector fields F, this integral FDR happens to be independent of path as long as C goes from A to B, regardless of how you get from point A to point B. It turns out the value of this work integral will be the same. All right, so the question is, for what functions are these the same? Okay, because what happens is, and I hope you can see the relationship between fact 1 and fact 2 here. If this integral happens to be independent of the path, okay, as long as the path goes from A to B, then what happens is we can actually solve for this independent of what happens between A and B, only at A and B, very much like this, the fundamental theorem of calculus, right? So in a sense, when we introduce this type of functions or vector fields for which the integral is path independent, okay, we can actually perform this type of subtraction to find the value of this line integral. And this is why it's called the fundamental theorem of line integral. All right, so with that as an introduction, let me define for you a couple of words here. Okay, now I'm not going to spend a lot of time on video writing down a bunch of words. You may stop, pause, and restart your video. So let me go ahead and pause this from my side so I can write these wordy expressions or definitions. Okay, so you may want to write these things down here as I explain. Capital F is a vector field, okay? Capital F with this arrow on top always means a vector field. Right now it's two-dimensional. This vector field is called, let's say this together, path independent. Path independent if this work integral, the value of the work integral, the integral of FDR over C, is independent of path, as long as that path C goes from A to B. Okay, so we are assuming, when I say path independent, that all the paths we are considering goes from the same starting point A to the same ending point or same terminal point B. Okay, so you may have the path C1 from A to B, another one from A to B called C2, another one called C3 from A to B. But as long as the path goes from A to B, regardless of which path you take or which curve you take from A to B, the integral FDR is the same number. If that's the case, we call that vector field F path independent. Okay, so that is a pretty explanatory term, right? Self-explanatory term. The F is called path independent. Okay, number 2, the vector field F is called conservative. Now, this is a very different type of word. It is based on conservation of energy in physics. But the capital F is called conservative if there is a real valued function, lowercase f, such that, and by the way, this is f of xy, two-dimensional for the time being. We can extend it to three-dimensional function later. But f such that its gradient is the given vector field. Okay, so in a sense, look at this. So if you take the derivative, gradient is a little different from the derivatives, but the gradient of f is really just the partial derivatives. Okay, so the derivative, roughly speaking, of lowercase f is capital F. Okay, so what this means is like f, lowercase f, is like the antiderivative of the vector field f. Okay, that's what this relationship is. Okay, now, so I am describing what is the vector fields that are independent of path independent, and vector fields that are conservative. All right, let me give you an example of conservative vector fields, and then we'll go into what that fundamental theorem is saying. Okay, let me give you this example here. F of xy is equal to x square y. All right, so remember how you take the gradient? The gradient of this function is 2xy, comma, and then x squared. Remember, this is, just because it's fx, fy, the partials form the gradient. And therefore, this is what we can say. If the vector field f is 2xy, comma, x squared, this is a conservative vector field by definition, because it is the gradient of a lowercase f, right, which is x squared plus y, or x squared plus y, x squared times y, or x squared times y plus any constant, right? And so in this case, the lowercase f, and I should have mentioned it up here, this lowercase f is called a potential function. It is also a physics term. A potential function, lowercase f is called a potential function if the gradient of this lowercase f is the capital F, a vector field. All right, and so here, should I mention this? Yeah, I'm going to give you the punchline, which is extremely important. The reason I mentioned the path independent vector fields and conservative vector fields together is because it has been proved, okay, and this is a theorem, it's a fact, that capital F, a vector field, is path independent if and only if, so it goes in both directions, capital F is conservative. All right, now this is a very important statement, all right? And you know that an if and only if statement, an IFF statement, is the strongest form of mathematical statement, because this means this implies this and this implies this. Okay, first, if the vector field is path independent, it is conservative, which means there is a potential function, fxy, such that the gradient of this lowercase f is capital F. Okay, in other words, it has an antiderivative. Capital F has an antiderivative, which is the potential function, lowercase f. All right, also, it means if f is conservative, then it is path independent. So it goes in both directions, which is what's so important about this. All right, so let me give you some examples in terms of the vector fields, right? Let's say I have, well, no, I've given you this, right? Is this vector field 3x squared y plus 1, x squared plus 2, is this conservative? What do you think? Is that conservative? Well, it's hard to tell, isn't it? Okay, it is hard to tell because the question is, does f have a potential function, lowercase f, and that is there a fxy, a real valued function, such that the gradient of f is equal to 3x squared y plus 1, x squared, x cubed plus 2. Okay, so that's a question. And you may just want to try to find something like that, right? Because, all right, so let's go ahead and do this. And this is the way to find potential function, if there is a potential function, right? You know that this has to be fx, the partial of f with respect to x. You know this is the partial of y with f with respect to y, right? So here is the idea. If f exists, now we don't know if it does or not, okay? What we know is that fx must be 3x squared y plus 1. And, important, both of them have to be true. Fy has to be x cubed plus 2, right? So let's see if we can find, and I think you can. I don't think I have to teach you a new trick to do this, right? I mean, it is sort of a new trick, but I think you can figure this out on your own. If the partial derivative of f with respect to x has to be 3x squared y plus 1, then f must have the form what? Well, after taking the derivative with respect to x, you have 3x squared y. So the original function must have x cubed y, right, plus x. Does it make sense? So again, you're basically taking the antiderivative of this with respect to x, thinking of y and 1 as constants, right? So 3x squared means that you have to have x cubed, whose derivative with respect to x is 3x squared, right? And y is like a constant, so you just add y to this. And then x, the fact that there's 1 here means there must be an x here. Now, there could actually be a whole bunch of other things. Okay, you could have sine of x, y, and log of y, and you could have y cubed, and you can have all sorts of y's, right? So you could also have, let's say, g1 of y, where this is a function of y only, no x, because as long as you have y and constants, this part disappears, right? So the antiderivative of this with respect to x happens to be x cubed y plus x plus some function of y, possibly. Now, also at the same time, f has to be of the form such that the partial of that with respect to y has to have x cubed plus 2. So that means you have to have x cubed y, right? Because that's the only way after you differentiate with respect to y could get x cubed. You also have a 2 here. So that means you have to have 2y. And then you can have any expression of, let's write this as G2, any expression of x without y. Because if you have, sine of x and e to the x or whatever, they all disappear after you take the derivative with respect to y. So my function, if this function f exists, it must look like both of these, okay? So can you think of a function of xy that looks like both of these? Yeah, there is something, right? So x cubed y plus x plus 2y. Now remember, x must be here because of this first condition. 2y must be here because of the second condition. Having x is okay under the second condition because that can be included here. 2y is okay because that can be included under G1, right? You could also have a constant. All right, so this is a general statement or general antiderivative, or more precisely, a potential function for capital F. All right, so this is an antiderivative, and therefore F is conservative because we found a potential function. You get that? So if there is an antiderivative or potential function, if there is a potential function, you can actually find it by integrating this first one with respect to x and second one with respect to y. Okay, that is the way that you are going to use over and over again in this section to find the potential function. I hope that's clear. Okay, and of course I'll give you something a little better idea for this as well. Maybe I should give you that right now. To check, how can you check f exists? Okay, all right, so I've already sort of mentioned this, but one way to find if f exists is to look for it, okay? Look for one. And if you find a potential function, guess what? Okay, if you find a potential function, then the capital F is conservative by definition. Now, sometimes you can't find this kind of f, okay? And so what happens if you can't find the lowercase f? Does it mean that capital F is not conservative because you can't find a potential function? just because you alone could not find a potential function in the first 10 minutes of your life, or first 10 minutes of your attempt to look for a potential function, that does not mean that the potential function does not exist, right? So how do you know that f is not conservative? After years and years of trying to find a potential function, you still can't find it. Well, that still doesn't prove that it's not conservative, right? Because somebody else in the next century could find it. So to check for to check if f is conservative, there is a test you can perform. Now, if you find it's conservative, then you will have to find a potential function this way. Okay, and so this method is actually very important. But if if it's not conservative, if it has no chance of being conservative, then you really shouldn't be looking for something that does not exist. Lots of people actually do that in life. They spend years of their life looking for things that do not exist. That's kind of sad. So let's not do that. All right. And so to make sure it's conservative, let me consider this. Right. Consider this kind of thing here. You know that f. Okay, what we want is f to be the gradient of lowercase f, which is fx fy, right? Well, guess what? You want this to be P and Q. That's our capital, F. Okay. So, so let's say if capital F can be written as P of xy and Q of xy, we're assuming this. Okay. So in order for a potential function, the lowercase f, to exist, this must be the same. Okay. Now recall, now we had some wonderful result. Okay. The fact that fxy must be equal to fyx. Now, this is true for almost all kinds of nice functions. In fact, for our purposes in calculus 3, for pretty much every function, lowercase f, that we consider, f of xy is equal to f of yx. Okay, so this is one of those things that we learned earlier when we talked about partial derivatives. So guess what? If this has to be p, and if this has to be q, then qx must be equal to py, right? Because p is fx. So fx times fxy has to be equal to fyx. So the derivative of this with respect to py has to be equal to the derivative of this with respect to x, right? So this is a necessary condition for that, right? So let me go ahead and write this down. If here's something important, if f is a conservative vector field, let's just say if f is conservative, then qx must be equal to py. Okay, and once you verify that, then you can look for a potential function which will exist. And by the way, if this does not, if this does not hold, okay, then there is no chance that such a potential function exists, so that you wouldn't have to look for it. Maybe I will also write this down. Okay, so if qx is not equal to py, okay, there's no chance that that f is, so no chance, okay, f is not conservative. Okay, so don't even bother looking for an answer, the lowercase f, because you will never find it. Okay. All right, so with that, let's go ahead and try this. Here's my example again. If f is x squared y and y cubed, let's find a potential function. All right, so you can start looking for a potential function like this, right? You know that if x has to be the first component, if y has to be the second component, take the antiderivatives and see if you can find such a potential function. After several hours, you probably will give up because you wouldn't be able to find it. Okay, and then you may wonder, is there a way to show that there is no potential function? Okay, all you have to do is to do this. Qx, what's the derivative of q with respect to x? Well, that's 0. Okay, and how about py? Well, that's x squared. right? So you know that these are not equal to each other, okay? And therefore, F ain't conservative. It's liberal or progressive, okay? No, we would not say that, okay? Nor do we say that F is a Democrat, okay? So capital F is just not conservative, all right, by the theorem here, which, by the way, that by definition means that the no potential function will exist for capital F. How about F is 1, 1? Is this conservative? Can you find a potential function for which the gradient of lowercase f is this capital F? Well, Qx, remember this is P and this is Q. Qx is 0 and Py is equal to 0, right? They're equal to each other, and therefore f is conservative. Can you find the potential function? Yeah, I think you can, right? In this case, you don't even have to really work hard. Xy would do that, right? Plus a constant. Oh, sorry, that is terrible, terrible. Because the potential function is not a vector valued function. Sorry, let me take it back. Okay, so if you want, this would be x plus y plus c. Would it work? The partial of this with respect to x is 1, and partial of this with respect to y is 1. And so that would work, right? So that would be our potential function. Okay. Yeah, let me, so here's the fundamental theorem of line integral. I guess I should use a different letter of different color for this. So let me tell you how this idea of potential function and conservative vector fields will help you find that line integral that we were talking about. And this is the fundamental theorem of line integrals. All right, so this is the central result in this section 6.3. The fundamental theorem of line integrals says this: if f is conservative, by the way, what does it mean? That means it has a lowercase f, a real valued function whose gradient is equal to capital F, okay? Then f is path independent and here's the crux of, here's the most important part of this. That integral, the line integral I was talking about, the integral of f dr, which is, by the way, integral p dx plus q dy. If you want to, mention a few other ways to denote this, but that's the work integral. This is, remember, it's independent of path, and it is f of b minus f of a, where the curve C curve C goes from the point A to point B. All right, so imagine we have this curve C, which goes from A to B, okay? And then this integral, as long as f is conservative vector field, as long as the C goes from A to B in any way, this way, maybe this way, maybe this way, maybe this way, whatever way, you go from A to B along a continuous line, curve C, the work integral would be the same, independent of the path. And the value of the function is potential function evaluated at the endpoint minus the potential function evaluated at the initial point. This is very much like the fundamental theorem of calculus, right? And that's why it's called the fundamental theorem of line integrals. Okay, so I am going to give you a quick an example or two, and then I think you can easily understand this one. This one is really, really not all that difficult. All right, so let me go ahead and give you a problem, and then I'll let you think about this. All right, example, example. First example, find this work integral, f dr on C, okay? And C is, let's say C is a line from, it's along this curve here like this, right? It goes from 1, 0 to negative 1, 0 like this, and F is 1, 1. Okay, now here's the old way of doing this. Okay, if you didn't have the fundamental theorem of line integrals, what you would have to do is to parameterize this curve. Okay, and you can go ahead. Let's parameterize this. You know how to parameterize this curve. This is supposed to be a circle, right? And it goes. Let's say it's cosine t, sine t, as t goes from 0 to what? Yeah, pi, okay? Because it's half the circle, semicircle. And then you find f, which is 1, 1, the derivative of r. Remember, you have to have the derivative of r in order to calculate the line integral. And that's negative sine t, cosine of t. And then we calculate f dot r prime because that's what you'll end up integrating. And that's negative sine of t plus cosine of t. All right. And therefore, the line integral from the line integral, the work integral, f dr over c happens to be the line integral from 0 to pi of negative sine t plus cosine t dt, right? Okay, and so then we take the derivative of the integral of this. So this will be cosine t minus sine t, or plus sine t, and then going from 0 to pi. Okay, so cosine of pi is negative 1. Plus sine of t is 0. Okay, and then minus cosine of, what's cosine of 0? That's 1. Okay, and then sine of 0 is 0. So this turns out to be negative 2. Right, so that's the old way of doing this. Now let's go ahead and apply, and maybe I'll let you just figure this out. Using the fundamental theorem of line integral. Right. So what is the answer here? Well, this is very simply f 1, 0 minus, sorry, f of negative 1, 0 minus f of 1, 0. Okay. Now remember, my f is 1, 1, right? We already found the antiderivative or the potential function of this. Okay, that, remember, was x plus y plus a constant, but we don't really need to do the constants, just like when you're trying to find the definite integral using the fundamental theorem of calculus. You didn't worry about that plus c, right? So x plus y. So all you have to do is write x plus y, and then go ahead and do negative 1, 0, and then 1, 0. This means you evaluate x plus y at this point, and then you do that minus this expression where you plug in 1, 0. So this is negative 1 minus 1, and that's minus 2. Okay, so that is, of course, the same as we found it earlier. And so that is how you can calculate this. All right, I'm going to give you another example and let you figure out how you may want to do this. And I will try to solve this in 2 different ways, but you can do this in the in any way you would like. Maybe you probably want to use the fundamental theorem of line integral. That would probably be easier. All right, so the curve is this. The curve C is from 0, 0 to 1, 1. It's a line segment. The vector field is 2xy comma x squared. All right, I want you to find, if you want to, you can do this in both ways, old and the new, right? Find the line integral over C of f dr. Okay, so try preferably both ways, but at least use the fundamental theorem of line integrals to find the value of this work integral of this vector field along the curve C. And I will see you in the beginning of the next segment of this video.